Greetings to all. So, in this lecture we will be discussing about one process of thermochemical treatment which is called carburizing. It means where we are trying to introduce carbon into the surface regions of the workpiece. So, we discussed in the last lecture the three possible ways we can harden the surface region material of a component. One is by the precipitation hardening, other one is by the solid solution strengthening, and by changing the phase of the existing material surface. That means like it is like initially a tempered martensite, which is a the martensite with a precipitated carbides. Now we will change that with a purely martensite. Okay. So, how we know that actually in the iron carbon system the martensite is the hardest phase. So, that is why we would like to have the martensite at the surface of the components, which provides a good wear and the good wear resistance. So, how we can do this process is that, so we take a let us look at first the iron carbon phase diagram. So, here what you see is the different phase fields of the iron carbon phase diagram, where you have the high temperature austenite field, right. This is all the austenite field, and then you have eutectoid reaction, that is called A1 temperature at 738 degrees Celsius, and this is as a function of mass percent of carbon, and this is the temperature axis. So, for a given temperature and the amount of mass fraction of carbon, we can actually know what phases are expected to be at the equilibrium condition, right. So, that means we heat very slowly and cool very slowly. So, now if you look at the temperature below 738, this region, and it shows that if you look at this portion, here it shows only very small solubility for the ferritic iron. It means it has a very small solubility. That means the moment you add a carbon beyond a very small limit, then you form actually the two phase mixture of ferrite plus cementite. Whereas, if you go to this condition of the austenite, right, which can take up lot of carbon into it. So, it is like at 1154 degrees Celsius, you see that it can take up about 2.08 weight percent of carbon, maximum amount it can be taken up in the solid solution, right. That means it will be a FCC iron lattice having carbon atoms in the interstitial sites. So, now if we have a, for example, a low carbon steel, so you have the low carbon steel component having certain microstructure. Okay. It will be largely ferrite plus a small amount of perlite. Okay. So, now if we want to do the carburizing, then objective is to have, if suppose this is the surface region, we want to have this to be martensite. Whereas, the bulk, this is the core, will be just like a ferrite plus cementite, or you can say that a ferrite plus perlite. Yeah. So, this is the kind of situation we want to have after the carburization treatment. So, how can we achieve that? Now, the issue is, let us say that because we know that lot of carbon can dissolve in the austenitic phase. So, if I say that this is the temperature axis, and then what I do is that, and this is where actually the A3 temperature, this is the temperature above which everything will be austenite. Okay. This is the A3 temperature, here it will be gamma, okay, phase single phase gamma, and then we take this sample to this region, okay, and then we introduce the carbon into the surface region. Okay. So, then what happens actually, if you look at actually the way the if you go from the surface into the percentage of carbon as a function of distance below surface. So, we generate something like this. Yeah. So, but if you see the microstructure, entire sample, that means if this is the surface region having the carbon enriched region, okay, this is the region having a high amount of carbon, and both are austenite, right. At this condition, this is also gamma, this is also gamma, okay. Gamma is for the austenite, but the difference is the amount of carbon is different at the surface region gamma, that means it has got a higher carbon than the carbon than the gamma which is below the surface subsurface. Yeah. So, now actually when you take such a composite sample, okay, and cool rapidly, okay, then you get actually the at low temperature, that means after quenching, okay, this means actually you do let us say the water quenching. So, then you get actually the surface region having a martensite with the underlying layer being the like a ferrite plus perlite. Now, you see that we know that when you heat up the sample to austenitic region, entire sample will be of austenite, right from the surface to the center of the sample. But when you cool it down by rapidly, only the surface region which is enriched with carbon is able to get the martensite. Okay. Why is it so? I think you all are aware of hardenability of the steel. Okay. We have a definition for hardness, which is a material property, and hardenability, it is the ability of the material to able to form martensite when it is cooled. Okay. So, how easily, like we know that in order to form martensite, we need to do a non-equilibrium cooling, that means we should cool the austenite to room temperature at very rapid rate. Now, how rapid, that means that is more rapid we need to cool, means that is more difficult, that means it has a low hardenability for that steel as compared to when you can cool slowly and get the hardness, that is a high hardenability. So, for the in order to understand this, okay, so we need to understand the so called TTT diagram or the CCT diagram. For example, you know the TTT diagram. What this 3 T stands for? Time, temperature, transformation. Yeah. So, what is this diagrams provide is you have a temperature as a function of time, and then you can mark the temperature, for example, this can be A3 temperature, right, and then you have a time scale. Actually, then you will see that the phase fields, when you get the different phases of the, for example, such a C curves can be seen. This is the gamma, this is also gamma, right, and this is a metastable gamma, because you see that below A3 it should have been not actually the gamma, single phase gamma. So, that means it is a metastable, above it is a stable gamma field. And these diagrams tell us that how you can construct such a diagram. You take a steel sample, take it to the austenitic region, that means above A3, and rapidly cool it down to, let us say, temperature T1, okay, and you hold it at this temperature, and then you start to see when it starts to form the, for example, the suppose if it is a eutectoid steel, then when it will start to form the perlite, right. That time will be given by this, that is a perlite start, and then if I keep it, then here the amount of perlite will be keep increasing and then it will be fully perlite. This is the perlite complete, right. So, this is where actually you have a perlite plus gamma, and then here you end up with fully perlitic steel. So, that is the connection of all these points, and you can do this at different temperatures, you get that. So, now actually some line will be there, that is called as a Martensite start temperature line. Okay. That means, if you can reach these points, okay, then we can produce the Martensite. Now, for example, in the carburizing we have a sample, okay. At the surface region you have, if I plot here the carbon content, then up to here this will be more, okay, and then it will be like that in the this one. So, this is also gamma enriched with carbon, this is a gamma which is having the carbon as in the initial steel chemistry. Now, these, if we want to produce the Martensite, for example, in this particular steel, so then we need to, for example, from this state we need to cool it at least, it should be the, okay, this should be the minimum cooling rate. This you see that this is actually the dT by dt, okay, that is the cooling rate, dT by dt, the slope of this line. This is the minimum cooling rate at which you can get the Martensite. If you are going higher than this, okay, smaller than this, then you will enter into this region where you produce actually the perlitic microstructure, that means you will not get the Martensite. So, however, these diagrams, okay, would known to have a dependence on the the steel chemistry, okay. How we can do that? Suppose for example, I have another steel having a more carbon than what has been shown here, that will have is okay, this is for steel with more carbon. Okay. Now, because it is being shifted towards the left. So, now the critical cooling rate or the minimum cooling rate to produce the Martensite is this one. Okay. This is for dT by dt for low carbon, and this provides the dT by dt for the high carbon. Okay. That means, when you are cooling it with this rate, suppose you are cooling it, and now this can be seen as like you have this surface region being this part, and these curves are for the core of the sample. Okay. You have a low carbon for which these are the transformation curves, okay, that is for this one. This region being high carbon, that has the transformation curve given by these lines. Now, when this sample, okay, this sample is being cooled rapidly, and now the cooling rate is suppose this one, okay, suppose you are following a cooling rate of, this is the cooling rate you are following, then for this cooling rate, okay, what you get is this can become Martensite, because you are cooling. Okay. So, I think I have just said opposite, okay. It is the reverse, okay. This is actually for low carbon and this is for high carbon, okay. I said it other way around. So, now actually this is okay. So, I will just change these things. So, now this is for the high carbon, okay. These curves are for the high carbon and these curves are for the low carbon. So, I just said it other way around. So, I hope it is clear to you that when you have more amount of carbon, these curves will shift away from the temperature axis, that means shift towards right, offering actually that. Now, when you cool this region and this region, let us say that have been cooled at the same rate, and for example, that rate is given by 1 in between. So, but this region is unable to because it has got its CCT curve here. So, now when I coal with this rate, for example, in between, then this region is unable to produce martensite, but this region is able to produce the martensite. So, in a way, by carburizing, what we are doing is we are enhancing the hardenability of surface region. So, because of this, after adding the carbon, because it has improved the hardenability, so by cooling it you are able to produce the martensite at the surface. This is what actually happens in a low carbon steel, where you have a core which is softer, and by adding this into the steel we are able to enhance the surface hardness by producing martensite. Now, on this right here, what is shown here in this plot is how the hardness of the martensite changes with the amount of carbon. It is x axis is weight percent of carbon, and how the hardness is changing. Okay. Here it is a Rockwell C-score, it is a diamond pyramid hardness number, okay, like this another means to look at the hardness. You see that initially it has got a very small increase in the hardness, but if you want to have a significant rise in the hardness, you need to have the martensite with more carbon, right. For example, our aim is to get about 60 Rc for the surface, then we should have at least about 0.4 weight percent carbon, right. So, that is where we need to have a martensite which is also having a decent amount of carbon inside. Our objective is not to get any martensite. A low carbon martensite will not have enough hardness what is we are looking for. So, that is where we want to actually realize a high carbon content to the surface. This provides two things. One is that it improves the hardenability, and at the same time when it forms the martensite, that will also have a higher hardness. So, these are the things one can realize from the carburizing. So, in this case actually we see that one issue, okay. When we do the carburizing, now the entire component has to be heated up to the austenitic region, okay. That means it will be entire sample will be like this, entire sample when we do carburizing is taken to the temperature where it is gamma, that is FCC, okay. And now when we cool it down after carburizing, when we are cooling it after carburizing, we are making the sample to be surface be martensite and the subsurface be ferrite plus perlite, okay. So, martensite, okay. So, I hope you are able to read that. So, due to this, because FCC being a much close packed structure as compared to BCC, ferrite or the body centered tetragonal martensite. So, you see that there will be a volume increase when we cool the sample after the carburization. You imagine that you have a big component, okay, let us say a very big gear, and we do the carburizing by heating up this entire big gear to the austenitizing temperature, and we know that we need to cool it rapidly in order to produce the martensite at the surface. And when we do that, entire sample tries to change its phase, and there will be a large distortions, that means it wants to actually change, and that can lead to a dimensional intolerance. You have made the gear has been manufactured with certain dimensions, right. Now, due to the heat treatment, okay, which we are doing like by carburizing and then quenching, we will introduce actually the dimensional changes. So, that requires again a machining, and even a component can fail because of the stresses being generated from this transformation. So, that is the one disadvantage of carburizing. And another problem is that, for example, you have a bulk microstructure that has been optimized by doing certain heat treatment and mechanical deformation. But now in the process of carburizing, you are killing all of it. It is like by heating the things to austenitic region means it is a reset button type. Okay. Whatever has been optimized, it all will go, everything will come to the austenite now. Now again it requires that we need to optimize again the bulk property. So, that is also another the disadvantage of carburizing. Okay. But it allows you to do very quickly because carbon sources are very cheap. Okay. That means and then so there are the limitations for every process. Yeah. So, keeping in mind these limitations, now if we move to nitriding, okay. So, whether this can be eliminated. Yeah. So, the nitriding employs the hardening for the surface regions by the precipitation hardening mechanism. Okay. So, what is shown here is the metastable iron nitrogen phase diagram. You see that metastable because here we all these iron nitrides actually are thermodynamically unstable. The same holds for the iron carbon phase diagram, which is also metastable whenever we introduce cementite in that phase diagram. So, now here you see that this is only a portion of the iron nitrogen phase diagram because you see that we have not gone to the 100% nitrogen axis. So, again you see here you have a ferritic phase that is only in this small region, right. This is the border for the ferritic iron. It has got a very low solubility, at the eutectoid temperature of 592 degrees Celsius it can only take a 0.4 atomic percent. Yeah, you see that this is given in atomic percent, in 8% it will be somewhere around 0.1, right. So, and the moment you cross this nitrogen solubility limit, you start to produce this gamma prime iron nitride. Okay. So, that is what is expected to happen when you take a pure iron, okay, because this is a iron nitrogen phase diagram. So, now actually we know that carbon the like in iron carbon phase diagram, here also gamma iron has a large solubility for nitrogen, right. So, like 10.3 atomic percent at this 650 degree Celsius. However, we do not want to go to this temperature. The reason being, this is what we are doing it with carburizing, where I am able to produce a carbon enriched layer that can produce martensite. Same thing can be done with nitrogen. You can produce a iron nitrogen austenite, okay, which is enriched with iron nitrogen. When you cool it rapidly, you produce a iron nitrogen martensite. Okay. That is not the whole purpose because that can be already done by the carburizing. So, how does this nitriding work? So, we do not want to have because we do not want to have any phase transformation of the bulk of the material. That means, if I can do the treatment like below this temperature 592 degree Celsius, the phase of the matrix will be simply the whatever is been fixed before, because there will be no transformations, because the for iron carbon system. So, it was that temperature. So, 738 degree Celsius is the eutectoid temperature, right. Whereas, for the iron nitrogen system, this eutectoid temperature is 592 degree Celsius, right. Because of this, this is being the higher than the eutectoid temperature of nitriding. If I do the nitriding at temperature less than 592 degree Celsius, so the bulk of the steel, okay, bulk microstructure of the steel, for example, is the bulk microstructure of the steel will not change, because in order to change that we need to go to this temperature. Yeah. So, now I want to only harden the surface region, okay, without changing the anything of the bulk. That is the case if I do the treatment at this low temperatures, right. So, you have a component which has already fixed its internal microstructure, bulk microstructure, and now I do not want to change anything of the bulk property. That means, I should not heat it up to too high temperatures where transformations can happen. Now, because it is a low temperature, nothing will happen there, but now how the hardening will happen, right. You see that again the solubility of nitrogen in the the ferritic iron is very low like the iron carbon, but one good thing about nitrogen is there are elements having huge chemical affinity to nitrogen. For example, aluminum, titanium, okay, vanadium, okay. There are the elements which have strong affinity to nitrogen to form, for example, aluminum nitride or titanium nitride or vanadium nitride. Okay. So, this is the provision which makes nitriding possible. Okay. So, that means if I have a steel, okay, which has got some of these elements being alloyed inside, okay, when I am introducing nitrogen, okay, when this nitrogen diffuses in, okay, a small amount that is within this limit, you can start to form these nitride precipitates. Okay. These form actually as a very nano sized precipitates of these nitrides. Okay. All these dots you can think of, these nitrides will develop, and that is where it leads to the precipitation hardening of this region. Okay. That means, it will remain as a ferritic. In the ferrite matrix you are able to produce these nano sized nitrides, and that will lead to the enhancement in the property. So, in this case after the nitriding you do not need to quench the sample, because we are not going to produce martensite, it is only ferrite. So, that means you can cool slowly. So, there will be less or no dimensional changes after the nitriding treatment. You see, this way you see that the disadvantages of nitriding what we have seen can be the overcome if you employ the nitriding treatment. So, this way we can actually optimize the process to give the surface hardness without changing the dimensions or the internal property of the core of the material. Okay. So, this is where we are having a precipitation hardening. So, we have discussed about also that another way to change the surface properties is to convert the surface region into a different compound of iron. For example, if you have a steel sample, okay, and you make the surface region of the steel sample being converted into a compounds or which are having a very hard and wear resistance. So, that is where this boriding treatment works. Okay. Boriding means we are trying to introduce boron into the surface regions of the material. That will change the microstructure such that it will produce layers of iron borides at the surface. Okay. So, it forms so called FeB and Fe2B layers, okay. And these layers are extremely hard and have a very good thermal stability. Thermal stability means when we heat up even up to 1000 degree Celsius, these layers will remain intact. Okay. That means, you can even do the heat treatment to fix the internal microstructure. Let us say that you produced this iron boride layers, and then you can still do the heat treatment of the bulk. That means, because you are able to go to the higher temperature. So, this is the disadvantage, for example, in case of nitriding. For example, you do the nitriding and then somehow you want to let us say change the microstructure of the entire bulk of the sample. that means you need to heat up and then to the austenitic region and then cool it down, and then where you lose all the nitrided region, because all the nitrogen will try to diffuse into the bulk of the sample. So, that is the becomes a disadvantage of the nitriding treatment, but in this case because these boroid layers are extremely the hard and they are the have a very good thermal stability. So, by having these layers produced, you can still do the heat treatments to the sample. So, this is a another dedicated treatments people employ to produce a highly wear resistant and these are also known to have a good corrosion resistance layers of borides on the steel surfaces. In this case also, because boron has a very negligible solubility in the iron. So, that is where actually it will not lead to much hardening by diffusion or dissolution in the matrix, but it will only produce these layers which are extremely hard. So, one may think that for example, in nitriding one can also produce layers of iron nitrides. Okay. So, there are two iron nitrides, it is called as a epsilon Fe3n and gamma prime Fe2n. Okay. We will go into those details of these structure and the properties of these nitrides when we detailedly look into that. But the difference from the boriding, right, if you look at the boriding and you have nitriding, in both cases you are able to produce some compounds of iron. Here it is iron nitrides and here it is iron borides. The difference is that these iron borides are quite stable as compared to these iron nitrides are metastable. So, if I heat up this the iron nitrides, they simply decompose, okay. They lead to decompose into iron plus N2 gas. Okay. So, you end up with simply a porous material, okay, with nitrogen gas filled pores. So, that is where once you produce these iron nitrides, they are also hard, but they have a very less thermal stability because they are thermodynamically unstable. So, you will not be able to have them as a very porous free layers, whereas these iron borides are extremely stable. Okay. So, that is where actually this kind of compound layers can be produced with boriding and with a good properties as compared to the iron nitrides. So, in the case of nitriding, that is why mostly people wants only the no compounds, but it is a alpha iron matrix with precipitates of alloying element nitrides, right. These are the nitrides of like aluminum nitride or chromium nitride or the titanium nitride. Okay. This is the kind of hardening people wants. Okay. Now, this is all about a sort of a quick overview of these three categories of thermochemical treatments. Carburizing, where we are actually producing a martensitic layer on the surface of the steel by introducing carbon into the austenite and followed by its quenching. This leads to carbon does two purposes. One is it will increase the amount of carbon that leads to whatever the martensite is forming will have a higher hardness, and same time it is also improving the hardenability, but with the cooling rate whatever you employ, it is easy to form martensite at the surface than into the in the core of the your sample. The other process which we have discussed is that because the carburizing has a disadvantages, that when you cool it down after the carburizing treatment, it involves the phase transformation of the entire sample, that means the bulk as well as the surface region, right. That involves a transformation from a close packed FCC gamma phase into a much openly structured BCC or BCT phase. So, this leads to a large volume misfits and the dimensional intolerance and localized stresses creation, because we are rapidly cooling, that can lead to the failure of a big sized components. Now, to overcome that, we need a treatment which can be done at a low temperature, that means where we will not change any phase of the iron carbon phases, like if I have some ferrite, it will remain as ferrite, it will not change to, for example, austenite. So, that is the case with the nitriding. You can do that nitriding at a below 580 or 592 degrees Celsius, and where if your steel contains elements which have a strong chemical affinity to nitrogen, such as aluminum or titanium. And then when you have these elements added into the steel, they will react with the nitrogen which is diffusing into the ferrite and form the nano sized nitride precipitates that leads to precipitation hardening. So, whereas often you want to have a surface treatment which allows you to also to do the further high temperature heat treatments of the steel. That means, whatever the phase you produced at the surface should be stable to go to higher temperatures. Okay. That is the case with the iron borides, which can be produced by treatment called boriding, okay, where we are introducing the boron into the surface regions which produces iron borides, and that improves the that provides a very good wear resistance, and they have a very good thermal stability. So, it can be used even at the components operating at a higher temperatures, or it allows you to do the heat treatments. So, with this now I want to conclude this lecture, and in the coming lectures we go into the details of these three processes. Okay. So, like what are the thermodynamics of the source of carbon, what kind of the atmospheres which are source of carbon can be used, or atmospheres which are source of nitrogen, or the atmospheres which are source of boron, and how to deal with this thermodynamic state of those systems. And then the kinetic part, that how fast the process runs, how that the reaction works, atmosphere to the surface of the sample, and then they should diffuse inwardly, and how to deal with those kinetics of the processes. Okay. Once we cover those things, then you would be able to appreciate that what are the controlling parameters which needs to be kept in mind while engineering the properties. Okay.